Now we are going to see some numerical based upon this amplitude modulation, where we'll see that how we'll draw this spectrum as well as how we'll calculate the power and how this percentage modulation and other factor is going to affect, as well as we'll find the Hilbert transform of the given function with the help of signum function. So still you didn't subscribe our channel, please subscribe it and share with your friend. The first question is here, this numerical about calculate percentage power saving when carrier and one of the side bands are suppressed in AM wave modulated to the depth of, so one time percentage modulation is 100, another case is the 50%. So here you are seeing that one of the side band and carrier is suppressed. That means it is the condition of SSBSC. So now this transmitted power general formula, what we have, PC into 1 plus m square by 2, where m is the modulation index. Okay. M is the modulation index that is calculated as AM by AC. AM is the amplitude of the message signal. AC is the amplitude of the carrier signal. So here modulation percentage is 100. So that is a percentage, AM is 100%. So that modulation will be 100 upon 100. That is going to be the 1. So that's why M is equal to 1 here. So once we substitute this value, we have 1.5 C. So this is the power which is being transmitted. But here carrier is suppressed and only one sideband is transmitted. So for that, formula is PC into M square by 4. So once we substitute M equal to 1, we are getting 0.25 PC. So how much now we are able to save? So we have transmitted 1.5. Now with the help of single sideband, it is 0.25. So that both are subtracted here and total transmitted power by this, it is being divided. So we have finally 83.3%. So this much power we are able to save. So already we know that when we are going to suppress the carrier, we are able to save the power. Second condition, when we have 50% modulation is there. So in case of 50%, M will be how much? Modulation index 50 upon 100. So that is going to become 1 by 2, that is the 0.5. So in place of modulation index, 0.5 is substituted, same formula of the transmitted power. So we have 1.125 PC. Now again, power in the sideband is the PC into M square by 4. So M is what here? 0.5. So we are able to obtain 0.0625 PC. Again, how much we are able to save? So transmitted power minus power in the sideband divided by the again transmitted power. So it is 94.4%. So this type of the question is very important. Okay. Now another question we have here. This is the most familiar question. A modulating signal is given by m of t, that is 2 sine 2 pi 10 to the power 4 t. So it is 10 to the power 4 is going to become here Fm is used to amplitude modulated a carrier wave by c of t 10 sine 2 pi 10 to the power 6t. So 10 to the power 6t is going to be the carrier frequency and this 10 to the power 4 is the message frequency. Write the expression for modulated wave. So we have to obtain the S of t and draw two-sided spectrum of modulated wave. So a spectrum question is many times they're asking. Okay, so this question is very important. So by seeing this, what is the message signal is given? M of t equal to 2 times of sine 2 pi 10 to the power 4 into t. And C of t is what? This value is 10 sine 2 pi 10 to the power 6t. So now if we compare with a standard signal, so in standard what we are writing? Am sine omega t. So omega is what? 2 pi. So this is for the m of t. So similarly a standard signal for C of t. Now if you want to write in terms of frequency, so AC sine 2 pi fct. So here if we will compare the value, so AM is 2, AC is 10, FM is 10 to the power 10 Hertz, FC is 10 to the power 6 Hertz. And this modulated formula of the modulated wave in case of AM signal, we need to remember. So that is S of t equal to, already separate lecture is available for all these topics, how we have obtained this expression. So we have AC into 1 plus KAM of t into sine 2 pi f ct. So that is what here omega c. So K is what amplitude sensitivity. So now M of t value is substituted here. So on the basis of that, this is K into M is going to become mu. Okay. And mu is what here? AM by AC. That is the modulation index. So amplitude of the message signal is 2. Amplitude of the carrier signal is 10. So finally modulation index is going to be here 0.2. So now in place of K into M, we are going to substitute the value of 0.2 and AC is the 10 and omega M, that is 2 pi FM. So FM value is 10 to the power 4 Hertz. Omega C, 2 pi FCT, that is the 10 to the power 6. So finally, this is the wave equation, that is equation for the modulated wave that we are going to transmit. Now to obtain the a spectrum of this modulated wave, we have to find the frequency domain of this modulated signal so that we can draw the spectrum. So now that expression of the modulated wave, we are going to separate. Okay, we are going to multiply with sine 2 pi FCT. So first term is we have 10 sine 2 pi 10 to the power 60. And second term we have 0.2 into 10 sine 2 pi 10 to the power 4t. Okay, another what we have sine 2 pi 10 to the power 60. So now here if you simplify this 0.2 into 10. So this is going to be the value of which 2. So this is going to be 2 sine A sine B. So that formula is being applied here. Sine A sine B formula, that is the 2 sine A sine B is what? Cos A minus B minus cos A plus B. So finally here, one frequency what we have? 10 to the power 4, another is 10 to the power 6. Okay. So this A is taken as the higher value, that is the 10 to the power 6 is taken as the A. This is the A, this is the B. So finally we have cos A minus B here. Okay. And minus cos A plus B. So now three terms we have. For this we need to obtain this Fourier transform. So if you see that in the standard, so finally, if you want to see that how we used to write, so this can also be written as 10 sine 2 pi FCT. Again, we have second term what we have cos, that we can write 2 pi into, that is FC minus FM into T. And third term we have minus again cos 2 pi FC plus FM into T. So now, if you see this here, Fourier transform, so how we are obtaining this one for as the impulse function and for the message. So that discussion was done earlier. So what we have? Del of. So here what we have in general, AC by 2. So AC is what here? 10. So 10 by 2. Then we have del F minus FC. So FC is what here? 10 to the power 6 plus del of F plus FC. So FC is 10 to the power 6. And here for this second term, third term, what we have? This is again 1 by 2. Okay, del F minus what frequency, what we have available here. So here what we have for the second term, if you see that we have 10 to the power 6 minus 10 to the power 4. Okay, so that is F minus. So this 10 to the power 6 become minus, 10 to the power 4 become plus. Again, plus del F plus what is the available frequency. That's why we have 10 to power, what we have here. This is F plus FC, one is F minus FC. Okay. So on the basis of this, we are able to obtain these values. Okay. So this is for the second term. This entire thing is for the second term. F minus FC, F plus FC. Okay. Now we'll go for the third term. So what we have here minus, so 1 by 2 del. So now here what we'll have? 10 to the power 6 plus 10 to the power 4. So F minus this. So both terms become minus, F plus. Okay, so that's why we are getting the value like this. So now if you substitute the value of this 10 to the power 6, 10 to the power 4, so here we are able to obtain here F minus 990, here F plus 990, Here F minus 10, 10. Here F plus 10, 10 means that is 1010. So now we got the complete Fourier transform. Okay. So what is the frequency here? You are saying that you have F minus Fc and F plus Fc. So this, okay, 990 and 1010 is going to be important for us. Okay. So now here we have one side for the positive frequency and side for the negative frequency here. So this is the F is given how much? We have 10 to power 6 hertz. So that is the 1000 kilohertz. Okay. And here Fc plus Fm, what we got 10 to 10. And here Fc minus Fm, what we have 990 kilohertz. So by this standard derivation, we know that this value amplitude is going to become mu AC by 4. So that value is substituted. So we have 0.5. Okay. So similarly here for the Fc plus Fm, what we have? Negative value. Okay. In the expression, we have negative. So minus mu AC by 4, it is the minus 0.5. So similarly, again for the negative frequency, minus Fc plus Fm. So amplitude is same. Again for this portion, we have negative value. So that's why it's coming downsides. At the frequency, carrier frequency, what is the value here? That is going to become AC by 2. So AC is what 10 here. So that we are obtaining as the 5. So everything we are getting from here. Okay. One is the upper frequency. One is that is the, like we have upper sideband, lower sideband, like this Fc plus Fm. Okay, so here what you're saying, this part is the minus. So for this only we have minus value. So for these two values, 10, 10, and this is again plus and minus. For that, what is the negative 1 by 2. So that is coming towards the downwards. Okay, and this minus Fc plus Fm 990. Okay, that is here upward sides. So that you are seeing here, the sign is plus. Okay. So for negative and positive frequency. Like this, we have a spectrum. So first we need to obtain the frequency, that is the frequency domain, that is the of that modulated wave. Okay. So frequency domain means Fourier transform. So by that time domain, that is the modulated wave. For that, we need to obtain the Fourier transform. Okay, that is a very simple, not difficult. Okay, for the carrier, we have del F minus Fc. For the plus F, del F plus Fc. One is the minus plus. Similarly, for the message signal, we have, okay, outside 1 by 2, then M of F minus Fc. Again, plus M of F plus Fc. Okay, like this we have. Now, third question is about, okay, one input, two AM modulator. So modulator means two signals. When we have one carrier signal, one message signal, minimum requirement is there for the modulation. So one input, two AM modulator is what? This is the 500 kilohertz carrier. So this is what FC with peak amplitude of 32 volts. So amplitude, this means this is the AC. The second input is the 12 kilohertz modulating signal. So modulating signal, baseband signal, message signal all are same. So this is what FM. Okay. And whose amplitude is sufficient to provide the plus minus, okay, BP, change in the amplitude of the envelope detector. So this is going to be the AM. So now they're asking USB, LSB frequency, modulation, percentage modulation, B max, B minimum, and output of the envelope and frequency spectrum they're asking here. So already we have seen how to obtain the frequency spectrum. So now upper sideband frequency is what? FC plus FM. So what we have 500 kilohertz, that is the FC, and FM is 12 kilohertz, so 512 kilohertz. Lower sideband FC minus FM. So the subtraction of this, that is 488 kilohertz. And modulation index is the amplitude of the message signal divided by amplitude of the carrier signal. So we have 14 by 32. So this is the value. Percentage means you have to multiply by the 100. So we are getting 43.75. And B max value is AC plus AM. What is the maximum? 32 plus 14 is 46. B minimum is AC minus AM. That is the 18 volt. So once we understand the derivation, then numerical will be easy. And when we have envelope, so this is the structure of the envelope. So this is going to be the B minimum part. Okay. and this is the B maximum. From here to here, this is the B maximum. So B maximum, how much we are getting? 46 volt. B minimum, we are getting the 18 volt. So same thing is here in the opposite side also. Now amplitude at carrier signal, that is 32 volt here, and amplitude of the USB mu AC by 2. So the substitute the value, we have 7 volt, and amplitude of the LSP is what here? 7 volt. So now we can plot this spectrum easily. Okay, like how we have seen, we are able to find in case of earlier case. Okay, so this is the everything is formula based. Just we need to understand the question what they're asking. Next question is about Hilbert transform. So Hilbert transform is very important in case of SSBSC signal. So they're having two pair. One is we call as the G of T, another is the G cap of T. Hilbert transform pair. So find the Hilbert transform of the X of T, where X of T is cos 2 pi ft means we have to find the X cap of T. So now we have to take the Fourier transform of X of T. So that is the X of F. And here, just like earlier, we have cos 2 pi ft. So this is the, here AC is what here? 1. So that's why it's written 1 by 2, otherwise AC by 2. Del of F minus Fc plus del of F plus Fc. Okay. So this is the for the cos. So now we have seen earlier how to find the Hilbert transform, Fourier transform. So that is the pair of the Hilbert transform. For that, Fourier transform is obtained by multiplying the Fourier transform of the given function with signum function. So signum function value is what? It is the +1 for the frequency greater than 0. It is 0 for f equal to 0. It is -1 for f less than 0. So it is multiplied by signum function to obtain the Fourier transform of the Hilbert transform pair. So finally, if you substitute the value here, so we have X of F, that is the Fourier transform of the X of T. And after rearrangement, we have 1 by 2j del of F minus Fc plus del of F plus Fc, and we have signum function. So now if you separate these two terms separately, what we'll get here? 1 by 2j del of F minus Fc signum function. Okay, again what we have? Plus 1 by 2j del of F plus Fc into signum function. So now this is for the positive frequency. So signum function value will be 1. And this is for the negative frequency. So signum value will be -1. So first term is multiplied by the 1. Second term is multiplied by the -1. So that's why here we are getting the sign minus. So this is the what we have, del f of minus fc minus del of f plus fc. That is going to be the, if you take Fourier, that is the inverse Fourier transform of this one. So we are going to get the x cap of t, and finally that is what? Sine 2 pi fct. So that is the Hilbert transform of x of t, what we have given, cos 2 pi fct. So that Hilbert transform pair, if you have to obtain, that is the x cap of t. So that is going to become sine. So cos become the sine here. So these are the basic numerical discussion related to the amplitude modulations, and these are the very important. So share with your friends. Any doubt is there, write in the comment box, like, subscribe. Thank you. Thank you very much.